After covering many of the important aspects of hydrogen, let's have a look at the application of it, and in particular now we will have a look at the use of hydrogen as energy carrier. The use of hydrogen as chemical compound will be covered in another lesson. When we have a closer look at how our energy is being used, we can see that the transportation sector plays a major role, making up more than 30% of our energy demand. This is a lot, but at the same time, this does include cars, heavy-duty and rail transport, shipping and aviation. This helps us understand why there is such a strong interest in sustainable solutions in the mobility and transportation sector. But at the same time, we need to also be aware of how heterogeneous this sector is. Other sectors, such as industry, except those listed separately, with 21%, and residential use, so the electricity and heating we use in our homes, with 15%, consume substantial amounts of energy as well. Now, all this energy is connected to carbon dioxide emissions if we rely on conventional energy supply. To prevent these emissions, we need electricity from renewable sources. And if we can't use this electricity directly and immediately, we need means to store this energy. Hence, the interest to use hydrogen as an energy carrier. Now, if we want to use hydrogen as energy carrier in various different applications, fuel cells are the technology able to convert hydrogen back into electricity. There is also the possibility to burn hydrogen in an internal combustion engine, but we will not cover this technology in this lesson. We have already covered the advantages of fuel cells in another lesson, but let us refresh our memory a bit. Fuel cells are efficient, reliable, and there are commercial systems available today. Though hydrogen storage and distribution are not without challenges, there are commercial solutions for these as well. And quick refilling of hydrogen tanks and the high gravimetric energy density can be listed as advantages for hydrogen as energy carrier. However, despite them being a mature technology, there are certain challenges, especially the supply chain, which includes raw materials, is not as well established as it is the case for many of the technologies we know and use in our everyday life. Depending on the application, the low operating temperature of the so-called low-temperature polymer electrolyte fuel cell also makes it difficult to reject the inevitably generated heat or the thermal integration. But let us have a closer look into what I mean by this and also into how far the commercialization of this technology is. To compare how far into commercialization a technology is, we rate them by what is called the technological readiness level, or TRL. A TRL of 1 would mean that the basic principles have been observed, whereas a TRL of 9 means that the technology has been proven to work in the actual application and in its fully developed form. As you can see here, for the selected application, the lowest TRL for fuel cells is 5, which means that the functionality of them has already been proven and validated. The highest TRL is at 9, so fully developed. Now, let's zoom in on fuel cells in the transportation sector. This includes automotive application, heavy-duty vehicles, airplanes, and ships. As you can see, while road transport, so cars and trucks, are fairly well developed, aviation and maritime application still have more hurdles to take. So why is this? Of course, one of the big advantages of fuel cells in all these applications is that hydrogen allows for true zero-emission propulsion. And in particular for cars, the relatively fast refueling times are an advantage as well. However, here, especially costs and the low volumetric energy density of hydrogen, even when compressed to 700 bars, is an issue. Also, the infrastructure here is a real challenge as demand is very decentralized. Infrastructure is of course also of concern for the heavy-duty application, but to a lesser extent because the predictability on major routes is higher. Costs and volumetric energy density are here of concern as well, but a major question is heat rejection, due to the high power demand of the application. As energy carriers are goods that are shipped as well, hydrogen is becoming one of them, and thus to use it in a maritime environment makes sense. However, the propulsion of a single ship alone requires enormous power, and with that, production capacities for the manufacturing of fuel cells. Besides this hurdle, the regulatory requirements due to the criticality of the maritime application are particularly stringent. Nobody wants a stranded container ship in the middle of nowhere due to failure of the power supply. The case for aviation is a similar one, though here there are in fact less alternatives. Low energy density and heat rejection are additional challenges. So all in all, hydrogen is an interesting energy carrier in the transportation sector. But for its use in ships and airplanes, there is still more to be done. Now, let's move on to the industrial sector. Here, the use of fuel cells has been tested more, and the relevant technologies have a higher TRL. The use of hydrogen in logistics has been tried and successfully demonstrated in the past. In particular, the operation of a fleet is here very beneficial. All in all, in an industrial environment, hydrogen infrastructure is often anyway a given. This hydrogen may or may not be of sufficiently high quality though, so there is a question mark here. Costs are, of course, here also highly relevant. When using hydrogen for the supply of the energy needed by industrial processes, the generated heat can be used as well, which of course strongly increases the overall efficiency. The low temperature is of concern in some cases here though. So now we understand why the use in the industrial sector is fairly highly developed. But what about the residential use? Here I grouped the power supply in handheld systems with the classic residential energy supply. As you can see, these applications have fairly high TRLs as well. Let's have a detailed look. Mobile chargers based on hydrogen fuel cells have been developed, but in comparison to batteries, they don't have that many advantages in this application. The distribution of hydrogen would be solvable, but the interest is not very high. In contrast, the use of fuel cells for the residential supply of energy is very interesting, with far more advantages. Similar to the use of fuel cells to provide energy for the industrial sector, here the generated heat can be used as well for heating and warm water. The latter we use all year. We also already have pipes connecting most houses to the natural gas grid, which comes in handy to either allow reforming of natural gas to provide hydrogen as a transition or to supply hydrogen directly. There are some regulatory challenges here, but they can be overcome. To conclude, hydrogen as an energy carrier and its conversion back into energy in fuel cells can help us to decarbonize some of the most energy-intense sectors. The technological maturity of fuel cells in these applications is high, but varies as the requirements vary quite a bit. Whereas we can see them as commercial products in residential use or logistics with additional advantages wherever we can use the heat too, there's more needed to make fuel cells viable as alternatives in shipping and aviation. This is not exclusively a technological challenge though, but it is also strongly related to the regulatory side.